sorry you couldn't be here. Right.
Yeah, me too. I would have loved to attend in person.
Yeah. So I'm quite happy to introduce our next speaker, Braxton Osting, who will be talking to us from Utah, and he'll talk about archetypal analysis. Yeah, please.
So thank you very much for the invitation and the opportunity to speak. So I'm going to talk about a couple different aspects of archetypal analysis. And so parts of the talk are based on joint work with Rujian Han, who's at the Chinese University of Hong Kong, Yiming Zhu, who's a graduate student at the University of Utah. And actually the bulk of this work is due to him and many of the ideas. Dong Wang was my previous postdoc, who's also at the Chinese University of Hong Kong, but in Tianjin, and Dominique Zoso, who's at Montana State University. Okay, so let me first introduce archetypal analysis. So this is an unsupervised learning method that uses a convex polytope to summarize multivariate data. So you're given data, there's endpoints in RD, and we're going to summarize this using a convex polytope with k vertices. So k is fixed, and the vertices we label with this capital A, like here. Okay, so we try to find the convex polytope, or equivalently the vertices of the polytope, to solve this optimization problem. So we minimize the mean squared distance between the data and the polytope, and we're subject to the constraint that the polytope, or alternative, the vertices are contained in the convex hull of the data. So I have here an illustration in 2 dimensions when I choose k equal to 3. So trying to approximate this data by a triangle, and the objective function, you can see this is it's the distance between the points and the convex projection onto the triangle. So the objective function is just the sum of all these squared distances divided by the total number of points. And the triangle can't be too large. It has to be contained in the data, in the convex hull of the data. So when we solve this problem, we label the point set A with a star to denote that's optimal. And when speaking, we say that anything associated with the optimal point set is are their archetype points. So the point set themselves are archetype points, and the convex hull of the points is the archetype polytope, or maybe the archetype polygon when the dimension is 2. Okay, so that's archetypal analysis. And so this was proposed in 1994 by Cutler and Bryman, and they proved several results. And so if k is 1, then the archetype point is just the mean of the data. So that's not very surprising. When k is between 1 and n, there exists this when the problem is. So existence of a minimizer is not unique, but that they're point set on the boundary of the convex hull of the data. And then for k greater or equal to n, the archetype point set, again, it's trivial. You can just take the point set to be the data itself, and so the objective is 0. Okay, so k, for this problem, in practice, you should choose k between 1 and n, and typically k is much less than n. So of course, you want to summarize the data with smaller vertices, right? They also demonstrated the archetypal.
Braxton, you're breaking up a little bit. Oops. It seems that the connection broke for a second.
Yeah, sorry about that. Let me reconnect here. Can you hear me now?
Yeah, we hear you well now. We just don't see the slides yet, but I think they're coming.
Okay.
Okay, we're back. Thanks.
Did I get to say that? Okay. Okay. Did I get to say that? Okay, so Cutler and Bryman, they showed that the archetypal analysis could be reformulated as a nonlinear least squares problem and solved using an alternating minimization algorithm. And this is efficient, at least for small d, n, and k. Okay, so I'll come back to this method later. And you might have also heard archetypal analysis is sometimes referred to as principal convex hull analysis, but I won't use this language here. Okay. So I presented this using the kind of the geometric formulation of the problem. There's also an algebraic formulation that looks like a non-negative matrix formulation. So if I stack the data into columns of a matrix, then I can write this as the non-negative matrix factorization problem of trying to approx x by x times AB, where A and B are column stochastic matrices. And well, the sizes of A and B, you have to pay attention to these. K has A columns, and so x times A, this ends up being the archetype points. These are convex combinations of the columns of X. Those are the archetype points, and then XAB, these are the projection onto the polytope. Okay, so this is completely equivalent to the previous formulation. Okay, so you might ask how archetypal analysis compares to other unsupervised learning methods that you might have heard of. It's very closely related to k-means. So in k-means, you can write it like this. And well, you basically comparing this to the geometric formulation of archetypal analysis, you just remove the convex holes, right? So I replace the convex hole with A, and I no longer have a constraint that A is restricted, A is contained in the convex hole of data. In terms of the principal component analysis that's used for dimensionality reduction, it's also closely related, and it's easier to see that from the algebraic formulation. So in PCA, you can write as also as a matrix factorization problem where U is as orthonormal columns, and so instead of using orthonormal columns, you have these non-negative matrix conditions. And so in particular, though, if K is less than N, then this is also a lower rank approximation of X. And so it can also be used as a dimensionality reduction method. So yeah, further comparison to other matrix factorization methods and clustering methods can be found in a very nice paper by Moore and Hansen from 2012. And so I'll refer you there. Okay, so let me give a quick example just to demonstrate this method. So I'm going to talk about COVID-19 data from early in the pandemic. So this is from May to September of 2020. And so the data I'm going to look at are time series and one time series for each state plus DC. So there's 51 time series of roughly length 100 corresponding to days. And this is a nice data set because it's very low dimensional. So if you do a PCA analysis of this, you find that 99% of the variance is in just the first two principal components. So yeah, so I can very easily visualize where each state is in relation to the others. And if I do archetypal analysis with K equal 3 vertices, I'm trying to find the optimal triangle for this data set. This is what I get. So I get this triangle on the left here. And then once I have the triangle, I can kind of transform into the archetype coordinates, right? I can just write everything in terms of the convex combination of the archetypes, and that's what's on the right. And so, well, one thing to notice is that sometimes examples will be at the vertices of the archetype polytope, and sometimes not. And so the nice thing about archetypal analysis now, though, is that I think about the examples that are near the archetype points as kind of extreme examples. And I can think about the other examples as convex combinations of those extreme examples. So people like archetypal analysis because it's a little bit more interpretable. And to show that a little bit more, here, if I look at the time series corresponding to states that are near the archetype points, I get these kind of, the color codes to different archetype points. And I get states like New York and New Jersey that had very high positivity rates in the beginning of the pandemic, states like Arizona that had a strong second wave, and then I have states that have kind of uniformly low positivity rates. Okay, so I can think about the other states as kind of in relationship to these extreme ones. Okay, so the first thing I want to talk about in terms of archetypal analysis is a consistency result. And there's been many this discussed at this conference already, so maybe I don't have to go into too much detail here, but I'll just say a consistency result. Everything I've described so far is, I think about now as kind of discrete archetypal analysis. And to set up a consistency result, what I need to set up a continuum version of the problem. So I think about my data now as sampled from some distribution, and then I solve the continuous version of the problem to find an archetype polytope. And then as I sample more and more data, I want to see that the solution to the discrete problem converges to the solution to the continuum problem. Okay, and so there's, of course, many consistency results for unsupervised learning. The ones I have some listed here for k-means and PCA, which are the methods that are the closest to archetypal analysis. And so these are already classical. Okay, so I've set this up already. So we're going to assume that x of I or IID sampled from a probability measure mu. And what I want to know is, for each n, I'm going to let an denote the optimal solution to the archetypal analysis problem for that value of n. And I want to know, is there a set A, which of course should depend on mu, such that an converges to A as n goes to infinity in some sense. And so, yeah, to identify the limiting problem, it's useful just to write the objective in terms of the empirical measure. So I can rewrite the objective like this. And since mu n weakly converges to mu as n goes to infinity, it's natural to consider as the limiting problem this one here. So I minimize this objective where I've replaced the empirical measure with mu, and now I've constrained the archetype points to be in the convex hull of the support of mu. Okay. So indeed, we do get a consistency result for this with this limiting solution. So yeah, for each n, this is already known to Cutler and Bregman, the archetypal analysis problem has at least one solution. So let's call it A of n. And our result is that A of n converges to A star along a subsequence in the Hausdorff distance, where A star is a solution to this continuous version of the problem. Okay, so the proof of this actually it just uses compactness in the triangle inequality. And then in addition, we can get a rate of convergence. So if you assume that the support of mu is convex, and actually we can relax this a little bit, but convex is sufficient. Then for large n with high probability, we have that the objective evaluated at the discrete solution is this is always greater than the one at the continuous solution, and the difference is bounded by this quantity. Okay, so the proof of this relies on some results from random geometry and Bedley's inequality. So it's a concentration inequality type of result. Okay. So here's an example illustrating consistency. So I have to have a problem where to illustrate this, where I know the solution to the continuum problem, and so there's not too many setups in which I know that. But if mu is the uniform distribution on the unit disk, then the solutions are regular k-gons inscribed in the disk. So that's something you can show. And so here you can see the solution is non-unique because I can rotate the regular k-gons inscribed in the disk. And so to see the consistency result, let's see. I can set k equal to 3, so I'm trying to find the optimal triangle. And I sample points from the unit disk and solve this for larger and larger n. And you can see that, the maximum and minimal angle in this triangle converge to pi over 3. Okay, so this is, this is what we expect from the theorem. Okay, so I'll say something about probability measures with unbounded support as well. So maybe it's clear already, but if you have a probability measure with unbounded support, then as you sample more and more points, the constraint that the archetypal polytope is contained in the convex hull of those points is increasing. So you can't really expect a consistency result without modifying the problem somehow. And the way we modify it, at least here, is to introduce a variance regularization term. So we add on to the objective function a parameter alpha times the variance of the archetype points themselves. So that's here. And okay, so for this modification of the problem, we also have a consistency result. I'll refer you to the paper for that. And we also looked at the behavior for large alpha. So when alpha gets large, you can actually show that all of the archetype points converge to the mean of the data. And they do so at this rate. And so we illustrate this here. This is kind of expected, I guess, too, because well, you expected the variance of the archetype points to go to 0, and they should be centered at the mean of the data. And so this is a very natural and expected result. Okay, so now I want to shift gears a little bit and talk about algorithms for computing archetypal analysis and the computational complexity of them. And so this is actually one of the limits of the applicability of AA to large-scale data analysis is because this is a very expensive problem to solve. I have to solve this optimization problem. This is like I said this, I presented this before as the algebraic version of the problem. And Cutler and Bryman already introduced this alternating minimization algorithm where I update A and B recursively. And so for fixed A, I find B that minimizes this problem. And if you look at this, B is, well, it's constrained to be column stochastic, so that's this notation. And actually this decomposes further. B, remember, is just it's the convex combinations of the archetypes that give you back the projection onto the polytope, right? So you can think about this as these are n k-dimensional QPs that you have to solve in this step. And then to update A is the convex combination of the data that gives you the archetypes. And you can rewrite this in the same form as in step 3, with using some linear algebra. And so actually, so here you get k n-dimensional QPs with the same. These QPs are all constrained. Okay, and so the complexity, if you look at this, is in step 3, you have n times the complexity of solving a k-dimensional quadratic program, and in step 4, you have k times the complexity of solving n constrained QPs. Okay, and so there's been a lot of work looking at accelerating AA, and some of these focused on improving the optimization methods, solving the quadratic programs. So people applied many different optimization methods here. And then there's also previous work on the inherent complexity. So some of this is empirical and some of it's more theoretical, relying on either random projections or core sets. Okay, so our approach complements these methods, and we combine two approaches to reduce the inherent complexity of the problem. So the first thing we do is we reduce the data dimensionality via randomized low rank approximations. So we think about this as kind of data pre-processing, which is reducing the dimensionality. And then the second thing is we reduce the representation cardinality by approximating the convex hulls of the data. So this is an acceleration step for step 4. And so both of these approaches, I'll show, have theoretical guarantees. And what's nice is that you can combine this approach with the above, the improved QP optimization methods here, or these kind of core set methods here. If you want to further speed this up. Okay, so these can be combined with the previous work. Okay, so first I'll talk about the data dimensionality reduction part of this. And so the main idea here is I want to find a low dimensional representation called x tilde for x. And okay, so the first thing I'll say is you should use a truncated singular value decomposition. And okay, so the problem here is that it's expensive if the dimension and the number of points n are large. So it's order dn times the minimum of d and n. And so you can use an approximated truncated SVD. So that's what we do. So if we can show that if you denote the optimal objective value of the problem by opt x, and we let x tilde be this is a rank P approximation of X, and it's up to a factor of 2. And so here's the definition of XP, what this 2 rank P approximation means. And then I'm going to let X tilde just be the part of XP in the UP coordinates. Okay, so that's the X tilde. If using this X tilde, I solve the archetypal analysis problem, I denote the solution to that by A tilde B tilde. What we show is that well, the objective function evaluated it for this A tilde B tilde is well, it's less than or equal to the best value you can obtain plus 8 times the P plus 1 singular value. Okay, and so in particular, if my original data was rank P, then this would be an exact approximation, right? Okay, so how do you obtain this X tilde P? Now you can use ideas from randomized block Krylov method. So this is introduced by Musko and Musko, and the idea here is to generate random matrices and form a Krylov subspace, and then do a QR decomposition, and you do an SVD there, and well, in the end, you cleverly put the matrices together to get an X tilde P. Okay, and so the Musko and Musko's result is that this XP tilde obtained like this is in fact a 2 rank P approximation to X with high probability. Okay, so this is the method that we use, and the nice thing is that this X tilde can be computed with this complexity. So remember before I had a min of D and N here. So now I've replaced this by log of NP. Okay. All right, so let's talk about the second reduction. And this is the reduction in the representation cardinality. So the main idea here is to use the extreme points of X as a dictionary. So remember, there's the archetype points, I only have to look at the boundary of the convex hull of the data. So if I only knew the extreme points of the data, then I could solve the problem. But the problem is, of course, that it's expensive to compute the extreme points of a high dimensional point set. And so the solution then is to select a few important extreme points for the representation. And so I'll say what important is, and then I'll say how, again, we compute these. So what we can show is that if you were to somehow be able to choose a subset of the data, so X of T is a subset of the columns of the matrix X. If I could somehow choose a subset of the columns so that the convex hull of those columns compared to the convex hull of the columns of all of X is small in the Hausdorff metric, then with using that subset of the columns, I solve the reduced AA optimization problem. So here XT replaces X in the usual problem. Then the optimal value here is less than or equal to 1 plus epsilon times the optimal value for the original problem. Okay. So let me say first how we select this subset T. So you can find X of T by random projections, and so this is these are ideas from Graham and Obermann, and the idea is that points that are more likely to be sampled in random projections are also more important in some sense. And so, very roughly, what I do is I choose I IID sample random vectors from the sphere, and I looked at the projection of the columns of X onto those vectors, and then I basically keep the columns of X so that obtain this largest projected value very frequently. Okay, and so you have to be careful about the number of columns that you keep, but okay, that's the basic idea. And with the theorem, what we were able to show is that if I choose m large enough, so m is the number of random vectors that I choose, then the distance in the Hausdorff metric between this Chausian's subset x of t and x satisfies exactly the kind of the bound that I needed as an assumption in the previous theorem. Okay, and so yeah, here you see the cursive dimensionality up here. Okay, and so okay. All right, so I'm going to put these ideas together now, and this is going to be this is our approximate archetypal analysis method. So the first thing I do is I use these ideas of Musco and Musco to find a reduced dimension data x tilde. And then I apply this random projection method x tilde to find x tilde t. So this is a subset of the columns of x tilde. And then now I finally solved this reduced archetypal analysis problem where I have x tilde t here. Okay, and so this problem, of course, looks just like the original problem, the original archetypal analysis problem. So when I say, any method that you use to speed up the optimization for this can be applied in this step here. Okay, and then from this a tilde b tilde, I can get back my my solution. Okay, and so what we can prove about this approximate archetypal method is that is the following. So under some assumptions, okay, I'll just say that well, the solution that we get a tilde b tilde a star tilde b star tilde, the objective value for those matrices is less than or equal to, okay, so it's a factor of 1 plus epsilon times the best value you can get plus 8 times the p plus first singular value of the data. Okay, and so the upshot of all this is that, well, if p and q are small, so I didn't say what q is, but if p is the intrinsic dimension of the data, and q, think about q as like the, it's more or less the size of the number of points in t. So if p and q are small, then the complexity of this method is going to be small. So in other words, yeah, x is approximately low. If x is approximately logarithmic and has most of the curvature concentrated on a small subset of the extreme points, then the overall complexity of this approximation is going to be low. Okay. So I'll conclude by showing some numerical examples. So here we apply the approximate archetypal analysis to first S&P 500 stock data. So we have about 2,000 days of stock data for 572 stocks. And we look at the cumulative log return of these data as a time series. And we're going to compare 3 different methods. One method is the method I just described, the approximate archetypal analysis method. One method is if I actually just computed the SVD and applied regular vanilla archetypal analysis. And then one is using there's an R package called archetypes for this. And we're going to repeat these experiments many times, and I'll report the average behavior. So the first thing I want to say, okay, so these are some archetypes for different instances of the method. And so you can see that the archetypes are stable in this method. The same time series are picked over and over again. If you compare, let's see, first the timing of these 3 methods, you find that the approximate method is much better than the other 2 methods. I think this is a factor of 60 better than using the original method with the singular value decomposition. And what is surprising is that, well, of course, the approximate archetypal analysis can't. So if I look at the residual, the approximate archetypal analysis can't do better than the original archetypal analysis, but it does much better than the R package. The R package does another approximation. So this is both faster and gives you better results than the R package. Okay, and so we also try to justify that the assumptions that we made in our reductions are hold for this data set. So indeed, the intrinsic dimension of the data is pretty small, and okay, so and then we looked at, here's a scatter plot of the reduced representation with the archetypes as well. Okay, and so as a second example, yeah, here's we look at 3,000 images. Each image is 150 by 150 pixels, RGB pixels, and we run archetypal analysis on this. And so this example is now big enough that we couldn't compare to like the R package or the simpler method. And okay, so here's it took about 600 seconds to run this. Oh, sorry, so about 6 minutes to run this on a standard laptop. And so these are the 10 archetypes that we get. And so these, yeah, these account for 44% of the total variance of the data set. And they are very different images. They were kind of extreme examples within the data set. So they're, you can interpret maybe the other images in terms of these ones. Okay, so that's what I want to say about that. And so just to conclude, so for bounded distributions, we identified a continuum version of the archetypal analysis method and a consistency result, including the convergence rate. For unbounded distributions, we introduced a variance regularized problem and established a consistency result there. And then, yeah, and then finally, we devised an approximate algorithm for large scale archetypal analysis, which enjoys theoretical guarantees. So if you have any questions, I'm happy to take them. Thanks.
Thanks, Braxton. All right, questions?
Thank you, Braxton. Very nice talk. So I have a question regarding, the choice of K. So, I mean, if K is, much less than D, I would expect that you're still doing K component PCA on top of the archetypal problem into the hyperplane or something like that. This is the first question, if you want. And the second question is, so if in the end, so in the application, what you want to get is, the limit, the limiting behavior according to the measure mu, along which you are, you are taking the samples like the images or the stock. So would it make sense to not, disregard maybe big N and taking just a few examples of what you have? So do not explore all the data. Also, if if you have maybe K is small, if K is small, maybe you don't need to use all your examples. Maybe using just randomly, in function of K, maybe you get the same statistical properties or something like that. So,
yeah. So yeah, thanks for the question. So yeah, it's true. Choosing K in this method is a little bit tricky, and it's trickier than principal component analysis because when you change the value of K, like if I increase K by 1, the old archetypes change, right? And so this is the beautiful property in PCA that, yeah, so this does not carry over here. But you're right, the observation that for K very small, we expect that, yeah, the archetype polytope is contained in the PCA space, in the subspace that the PCA gives you, or at least is close to it. Yeah, and your comment about throwing out unimportant data points, that, I mean, that's I think this is somewhat what we do when we compute X of t, right? This when we reduce the representation cardinality, we're trying to throw away points that are kind of in the interior of the convex hull of the data. In fact, more than that, maybe we'll even throw away extreme points if they don't have large curvature. So I kind of gloss over this a little bit, but yeah, there's an interpretation in terms of the points that we keep in terms of curvature, and yeah, we throw those away too if they don't have large curvature.
Thanks, Braxton. Are there any further questions? Just a brief question on my side. Are there some estimates on how far is this from PCA? Let's say when K is small, right? K is 3, how far is it from the plane? Could one obtain some estimates on that?
Yeah, I think that's a nice problem. I haven't seen estimates like that. Mm-hmm.
Yeah, we're a little bit kind of running late, so we're gonna stop here. Let's thank Braxton again. And we come back at 11:15.